Bonjour everybody, so welcome back to another video. Today's first question is, find the length of the altitude from B to segment AC in triangle ABC below. So, don't judge on how straight my line is because I am not a straight line drawing robot and I am drawing this by hand. That is horrendous. It gets the job done, okay? And this is a 90-degree angle. So I'm going to be introducing two ways that you can actually do this problem. The first way is slightly longer, and this uses similar triangles. So as you guys can see, I'm just going to label this D and E because, ABCD, why not? So I'm just going to label these 2 points D and E. As you guys can see, by drawing the altitude from B to segment AC, I've basically created the side for a whole new triangle, aka triangle BEC. So if you want to use this method that I'm about to show, which is like a similar triangle ratio kind of thing, you have to prove that these two triangles, and by these two triangles I mean triangle ADC and BEC, are similar. So how are we going to do that? So triangle BEC has to be similar to triangle ADC. And in this case, you guys can see that since both angle E and angle D are 90-degree angles, this means that E and D are equivalent. And since they share angle C, this means that they have two angles that are the same, therefore making them similar. So this means now that we know that these two are similar, we can find the 2 points that correspond to each other. And in this case, we have this side corresponding to this side, and this side corresponding to this side, which we're just going to label H for height. So that means that now we can draw a ratio. This means that H over 8 is equivalent to 5 over 6, and from then on, it's just smooth sailing. So 4 and 3, so 3H is equivalent to 20, therefore H is equivalent to 20 over 3. And this is one way that you can do this, but the other way that you can do this, which is slightly more conventional, is by using area. In the same format, as you guys can see, since it's already told you the height and the base of our original triangle, which shares the same area as our sort of flipped triangle, in which H is our height, this means that since the area of a triangle is half of height times base, so half of 5 times 8 should be equivalent to half of H times 6. And using this, we can also solve for this because these two both even out. And now we just get 5 times 8 is equivalent to H times 6. Therefore, 40 is equivalent to 6H. Therefore, H is equivalent to 40 over 6. And if we simplify this, we'll still get 20 over 3. And they share the same answer, but they are just two different methods. You guys can choose your favorite, whichever one's more efficient in your situation. Like I mentioned, the area one is usually more conventional, but the similar triangle one is also used quite often. Moving on to problem number 2. What is the greatest number of points at which a circle and a hexagon can intersect? So as you guys can see here, I've already drawn a pre-made hexagon. However, this hexagon is not very perfect because this OneNote does not have a hexagon drawing tool, so it's just a collection of straight lines. So, if we think about this, the first thing that comes to mind is probably fitting the hexagon into our shape. And this is extremely hard as, just like I said, our hexagon is not very perfect. But just pretend that our hexagon's tips, our vertices, are perfectly touching. So wait, let me just reselect this. Just perfectly touching the insides of this circle, which they are not, as you guys can see. However, just go along with it here. So, as you guys can see here, this means that there are exactly 6 points in which the circle and the hexagon can intersect. However, this is not good enough for us, because we are trying to look for the maximum amount it can go. So, if we look for that idea, if we expand it even more, so that only the sides here are just very barely touching, and that it looks like it's about to eat the circle, however, it's not, And if we expand this anymore, it's just going to take over the circle, and there are going to be no points touching. But since if we go just like this, and each side touches the circle once, that's also 6. And you might think, oh, well, then the maximum amount is 6, right? However, if we shrink it so that it just has the best of both worlds, so that each side touches it exactly 2 times, like so, we'll actually get, oh, that actually fit right pretty perfectly. But we'll actually get 2 points in which it touches on both sides. Therefore, here, 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 and here, and here. And obviously, this means that this is the greatest amount as there is 2 on both sides, basically like combining the best of both worlds. Therefore, 2 times 6 is 12, so the greatest number of points in which a circle and a hexagon can intersect is 12. So yeah, that's the end of this video. I hope you guys enjoyed, and I hope you guys learned something new, and I will see you all on the next one. Bye-bye!